Okay, well, good morning, everyone. Welcome to EECS 251B, Advanced Digital Circuits and System. Today, we're going to talk about design productivity and some of the very interesting methodologies that we're having to make the design process faster and also more efficient in some way. So before we get there, I know Bora likes to do this kind of interesting news of the day or some like interesting historical moment related to semiconductor industry. So this day we talked about earlier, as before the class. So we talked about briefly the Microsoft acquisition, but more related to the semiconductor industry. Something interesting is going on. Actually, last week. Like Intel announced they're going to actually build a large fab in Ohio here in the United States. It will cost more than $20 billion here. So it is really interesting. We'll talk about the fab industry later, and also we mentioned earlier the consolidation there. It's interesting to see. Also very exciting, actually, investment here in the US. Companies like Intel. At this point, Intel is actually the major US fab here, are actually investing very heavily and have very interesting strategy in really thinking about not only hardware, not only just the fab, but also like across the stack, what they call a scale manufacturing, doing both software, silicon platform, and also very interesting packaging and different design process actually innovated at Intel. So it's really interesting. We'll see more activities here, of course, across the world, but also here in the US in really using different technology drivers and thinking about more advanced integration to actually build very more complex system and also very, very cool actually system in a way. Of course, any kind of industry, there are like a range of different factors, but from pure technology point of view, it's interesting to see all the different activities here and also see more excitement across the world with the semiconductor industry. So with a lot of the topics that we covered here in this class, many of them are very applicable in actually building future really complex digital or mixed signal also systems with different technologies here. So with that, a lot of excitement, a lot of interesting activities. With that, let's get today's lecture started. See, I can advance. Okay, just a quick review. We just finished the first week of the semester. Hope everyone had a fun beginning of the semester, and we're looking forward to get to know each other in person, hopefully very soon. So we covered Chipyard, very a powerful way actually generate RISC-V based SoCs and help all of you get started on your lab one. It's really just to get you more familiar with the infrastructure so that you can really use this infrastructure, especially towards the end of the semester when you actually start doing your project. Think about all the different things that you can potentially do with the RISC-V, the Chipyard infrastructure. There are a lot of components already existed, but you also have a lot of flexibility to do either circuit level optimizations or adding different hardware architectural components onto the Chipyard ecosystem. Although this is very early, it's still beginning of the semester, but really think about your project, what you can do with the infrastructure that we introduce in this class. So in today's lecture, we will actually be transitioning to what we call, I guess, design methodology or design productivity module. It will roughly, the entire week, we'll talk about the different methodologies or different ways that people are using today in building a digital system. Many of you are already very familiar with Verilog or VHDL, depends on which one you like better, right, in doing actually digital system design. But here we're going to introduce a couple of different alternatives people are using. The goal here is really to raise the design abstraction so that we can actually finish the hardware design, both design and verification faster. We're going to introduce a couple of different design, I guess, alternatives from not really high level to low level, but basically both are higher level abstractions. But different from Verilog or VHDL, there are also some other methodologies are being very popularly used today. And different user, different designers, different engineer has their own preferences, but we like to actually do a quick like overview so that you see some of the examples there and get interested in some of the methodologies. And in particular, we'll also spend a little bit more time on Chisel. We also have a guest lecture, Hassan Genç, later part of this lecture, who will also cover some of the motivation behind Chisel and some of the powerful things that you can do with Chisel. This will also help you navigate lab 2. We're going to introduce a pretty simple, a small Chisel lab so that you can also get some more hands-on experience with the Chisel flow, the Chisel language, and also be exposed to some really interesting new design methodologies that existed today. So we'll start with some like overview of the way we think about design productivity. I'll do a brief introduction of high-level synthesis, another way of raising the design abstraction to a higher level. And then Hassan will actually cover the Chisel part of the lecture, talk about some of the Chisel advances, both advances and also some of his personal experiences of using Chisel in the development process. And next lecture this week, Bora and Vignesh will talk about system Verilog, how it can be used in design and verification process. So the different languages, different approaches with the goal of raising the design abstraction. With that, let's get started. So design productivity, some resources. So this lecture will be mostly focusing on the Chisel and high-level synthesis. So here are some resources we find very useful when we actually navigate the design process. So if you are interested in any of them, start from here. And if you are also have any questions, feel free to reach out to us. So just some very quick brief introduction, right? So this is, we already mentioned earlier, with all the different excitement in the semiconductor industry, it is really exciting time when we think about hardware design in general, right? So we are seeing interesting hardware being designed, not only from traditional hardware companies like the Intel, AMD, NVIDIA part of the world, but also from software cloud system companies like Microsoft, Google, Amazon, AWS, part of the world, and also like all the different startups, right? They also have very interesting ideas, and they have the I guess both the investment, they have the money, and also the expertise actually developing really cool, really interesting system, especially in the deep learning space, right? We see a range of different system, hardware, specialized system being developed for different applications. So it's a really interesting time. We see a lot of investment, excitement in the hardware design. We will also get a lot of programmers, engineers excited about hardware design, right? So all of them will be actually start the hardware design process and understand all the different trade-offs in the hardware design. So with that, we really also need to think about the complexity of today's system, right? So if we think about this is already, I guess, a couple of years old. We think about the modern SoC, right? This is NVIDIA Xavier system, right? So of course it's from NVIDIA, so it has GPUs. There are also a CPU block as a part of the SoC. Also have a range of actually accelerators, deep learning, DSP processors, vision accelerators, and camera processing. So there are a range of different hardware actually being integrated into the system. So when we think about this system, it's not only just CPU or GPU, right? There are a range of different IPs, different accelerators, co-processors, all of them actually need to be integrated onto this platform system on chip, right? So this, again, this is already a couple years old, right? But when it was first announced, the headline is, this is basically the most complex SoC people ever made. It takes roughly 8,000 engineering years, right? So it's like a lot of engineers. You think about, we actually need to actually roll out this kind of processor every other year, right? So a lot of engineers are actually participating in the design process. A lot of different flavors of hardware are actually being designed to to fulfill different requirements from different applications. So with that, so it takes a lot of effort, right? Where do we actually spend those design efforts if we think about design process? By the way, if you have any questions or anything you'd like to share, feel free just unmute yourself or use the chat box. I'm also monitoring the chat window right now. So again, some interesting data point when people actually approach design effort, right? So if you think about all the different like accelerators or new features that we want to implement either on CPU or GPU, right? It takes roughly like 2 to 5 years from the initial inception of idea when we start the R&D process to the final productization when we actually get the final product, right? It takes roughly 2 to 5 years. Again, depends on the feature complexity. Some features are more involved, require a lot of integration or interaction, not only with IP itself, but also with other systems. Some IPs are more standalone. So once you have the IPs, just plug in and we're done, right? And then we look at the development part from the R&D to the final product, right? So roughly, like I guess architecture and the implementation are like half a half, right? So people do some high-level exploration, understand the architecture, different architecture and microarchitecture components, and then once they start the implementation, so here implementation includes both design, like implement the design, but also verification. Verification actually takes a lot of time, just making sure that we're building the right design, the design actually behaves as expected. So a lot of complexities, a lot of actually efforts being spent in really design and implement the hardware. So I guess people are talking about the golden age of hardware, semiconductor industry, and all the different domain specialization, heterogeneous integration. But in reality, when we actually think about the complexity of our system, really the number of unique features that we could actually implement in hardware is really more limited actually by design and productivity design effort these days, instead of just thinking about like the standard metrics, power, performance, efficiency, right? So that's really just a high-level message we like you to think about when people actually approach design productivity, design methodology. There is really a very practical reason here, right? We want to get our hardware out faster. We want to get more designers, hardware, software designers to enjoy, to have the opportunity to build cool systems. And to do that, we need actually more interesting and also high productivity design methodology here. Just one quick note, again, hardware getting faster, it takes effort to actually build hardware. And again, software also, like algorithm also changing very quickly, right? So we are seeing new algorithms, new innovations in the algorithm space already at a daily scale or maybe even hourly scale. Every hour, like new ideas just keep popping up. So to actually like we talk about the 2 to 5 years cycle hardware development, we really want to actually shorten it, right? So that we can actually the hardware system can also be more adaptive and we can actually build interesting hardware system quickly for those applications. So with that, just a quick intro, that's all the really the motivation, right? When people actually start thinking about design productivity, we need new methodologies so that we understand the design trade-off, understand all the different complexities for individual IPs, especially for more specialized IPs. There's also a more like iterative hardware software co-design process involved. So with that, we really want to really think about design productivity and how we can use new methodologies to make the hardware design easier and faster. So with that, we're going to show, again, like 3 examples, 3 different alternatives when people actually approach the design, improving the design productivity, also improving the design effort process. But before we get there, any questions and comments from the audience, from everyone? Mm-hmm. Okay, well, great. Let me see. Okay, so we'll do a very brief introduction of high-level synthesis, which is a very interesting design methodology people are also using. It is an old idea. People started doing high-level synthesis in the 90s, so it has been around for a while. More recently, has more we see actually more efforts in really applying high-level synthesis in production. So we'll have a brief introduction of high-level synthesis, what it is, what it can do. Again, don't worry too much. This is just a pointer so that you can actually start exploring. There are also, like we mentioned, a lot of resources in the beginning. So there are like a lot of opportunities to give it a try, give the tool a try to see whether you like it or not. So again, a lot of those design methodologies really thinking about what this kind of like design, thinking about design abstraction, right? So when we think about the EDA industry, how we actually from really reason about transistor level complexities to gate level, and now state of art is really the register RTL level. It has been around for a while. This is still the main level of abstraction when people actually approach hardware design, right? Those very, I guess, classic question at this point for the EDA industry is that, okay, we have been at this RTL level for a while, right? So what's next? How we actually can go higher level of the abstractions, but because typically we go actually higher level abstraction, the design also get easier. We can compare like gate level design to RTL level design, right? So it's actually faster, easier, improving the productivity, but also means more EDA tools, more tool involvement, and also complex to different advances in EDA algorithm need to actually facilitate the development, right? So the goal here is really whether we can improve, raise the level of abstractions above the RTL level. So the response to that, is high-level synthesis from the EDA industry. Again, it is a relatively old idea. It has been around for, at this point, 20, 30 years, right? So it's really very intuitive approach to hardware design, right? Whether we can actually automate the design process. So instead of starting from RTL level, which is still the standard, right? So whether we have the opportunity to raise the level of abstraction so that we can start from some higher level programs like C or C++ and use more a compiler oriented approach to generate RTL directly. So here, again, people are different, like high-level synthesis definition is pretty broad. It's basically an automated design process, but in practice, when people actually mention high-level synthesis, typically it means start from C or C++, basically C2 RTL, you can think about that as a C2 RTL compiler. So instead of doing all the designs at the RTL level, whether we can design, maybe also some of the verification at the C or C++ level, and then using automatic transformation, more like a compiler flow so that we can actually compile those programs to RTL. So the benefit is, yeah, why we want to do that, right? We already talked a little bit more, we want to raise the design abstraction, right? So a core benefit or core motivation is really to actually to improve the design productivity. That's the focus of the lecture, right? So to lower the design complexity and also to have faster simulation speed, right? So instead of doing all the simulation at the RTL level, we could actually simulate at the C, C++, or more specifically, really system C level to do the simulation, which can actually have a faster feedback cycle for designers to see whether there are any functional issues or design issues, performance issues that we can also fix the code quickly. And again, it's also for portability. We'll talk a little bit more how high-level synthesis actually expose the design space with different pragmas, different ways to actually expose the design alternatives. So then you can think about like more like a compiler, you have a C code, but then to actually get different version of hardware, you can basically have different flags there, either O1, O2, or O3 that actually apply different transformations, so I can get different RTL. So that also applies in high-level synthesis. You can add different pragmas there, different arguments in the compilation process to actually get different optimization so they can evaluate different design process. So that's related to the design space exploration. So a lot of I guess we don't see that much these days. Maybe 10 years ago, 10, 15 years ago, a lot of research on high-level synthesis is doing basically this design space exploration. We talked about the different alternatives there, right? So with design space exploration, we can get higher QoS or QoR quality of result in the design part. And the goal, again, is to shorten the design cycle. So back at the video, when I was participating in also a team effort in doing high-level synthesis research, one of the benefits we experience is that we can do this kind of what we call basically daily spin of design from all the way from C++ to RTL to gates and then to GDS in 24 hours. So we can get different feedback in the design process. Basically, we fix bugs, do changing designs in the morning during the day, and then start our regression overnight. And then first day in the morning, we can also check our report, and then we see there's any issues, so we can do another iteration every day. So that has been very useful in our own design process to actually get the design faster, where we can do a lot of iteration at the C++ level instead of doing RTL iteration. So that's the benefit of high-level synthesis. Again, some examples or some pointers on how we can actually use high-level synthesis to do the hardware design part. Let me see whether I can. Oh, I cannot erase this. See. So before we move on, any questions, comments? Okay, great. So just a simple example, right? So so if we think about just a very simple counter design, right? So here is a standard, I guess, module when we actually do Verilog, we specify the different inputs, have an always block, and then start the incrementing part, right? We do actually in untimed C in basically using high-level synthesis-based approach. It's basically very similar to the way we actually write a C code. We just say, oh, we have a outside integer, and let's increment it by 1, and then we can actually the tool will automatically synthesize it to be a counter. Again, this is a simple example. We have a little bit more complex example later, but this is basically the goal of high-level synthesis, to do this kind of automatic synthesis or automatic compilation instead of writing RTL code. So I noticed so Hassan will also use FIR filter later part of the lecture when he introduced Tresol. So I think it might be fun actually to also do a FIR filter. Again, quick exercise, like to see how it actually implemented in different languages. Again, all those languages, the goal here is to improve the design productivity. So this is a C version. We could also do a C++ version of the FIR filter, but let's do a C version because I find this pretty interesting to compare different design. So again, so this is a very standard FIR filter. So we have an input signal. We have I have a coefficient constant, right? So during the FIR transformation, we basically, so this is basically directly translate this equation to a nested for loop so that we can actually calculate the output by multiplying the coefficient with corresponding input. So this is the design, and this is the C implementation of the design, right? So if we think about we turn this into hardware, right? So we also want to actually generate FIR filter hardware block. The design, at least when again, this can also be directly synthesized with high-level synthesis. This is synthesizable, so they will actually generate a design. The way I like to write the design by high-level synthesis, or again, different designers have different styles. I actually like more just explicitly to expose the hardware structures there. So it's still writing, again, even with high-level synthesis, we're still writing hardware here. again, it can be potentially used by software designers and compile software directly. That's one way of using hello synthesis. But there's another way of using hello synthesis more, at least closer to a hardware design, is that we're still exposing hardware. Like a very simple example, we're still exposing this coefficient with this kind of shift register here. So we still have some notion of the microarchitecture of the design. It just, instead of using like Verilog or VHDL to describe the hardware, we are actually using higher level language, C or C++ here to describe hardware. In this case, at least when I read it, I still like to instantiate this shift register here. So this will be our shift register block, and talk about and also explicitly talk about the shifting behaviors, right? How this shift register behaves, right? With, again, with a simple for loop, and then we have our for loop doing multiplication to do the FRR coefficient, right? So this, if we just do this without any pragma, anything, this can be directly synthesized to basically a sequential implementation of the FRR filter. Have a multiply, like a multiply and accumulation here, and then store the result to our local register, and then we have a shift register, coefficient register. We actually get data here. So this is basically a sequential implementation of the FIR filter. You actually, when you hear people talking about high-level synthesis, or when they actually apply high-level synthesis in the design part, you always hear people talking about all the different pragmas, what they do mean when they do transformation. There's nothing really anything more complex with those transformations. Very standard. It's basically whenever there are loops, there are parallelism, how we can actually expose those parallelism from the C++ code to hardware. So basically, it's always, again, there are a range of different pragmas if you actually go through the Vivado menus if you're interested. But in general, three of the most commonly used pragmas in hollow synthesis design is typically very loop focused. It's basically trying to expose parallelism in the design. It's related to unrolling, loop unrolling. We have the example in a minute. Partitioning, basically have more ports or more basically direct accesses to the design and to the hardware. And pipelining, this is basically pipeline the design so that we can actually have a higher throughput in the design. So it's always those three major optimization. We'll have an example, just briefly go over those. All of this is just to help you navigate when you actually see a hello synthesis design. There's nothing too fancy about it. It's pretty straightforward, just those standard optimizations. Before I move on, any questions, comments, anything you want to share? Clear? Okay, great. So like we talk about different transformation, right? So one thing you will see a lot is this kind of loop unrolling. Again, this is basically, I mentioned earlier, right, to expose parallelism. Whenever we have loops, right, there are opportunities of executing those loops in parallel here, right? So you will see this kind of pragma, this unrolling pragma. Different vendors have different ways specify this pragma. This is a more like Vivado, like Xilinx way of specifying those pragma. So it's basically unrolling. So before we have this kind of sequential execution of this MAC unit, right? So now I want to get more parallelism, right? So now I have a more parallel version by unroll the loop so that I can do those MAC right in parallel. So this is one way to actually introduce parallelism by having multiple parallel function units. So again, all those pragma have hardware implications. So it actually changes the hardware behavior. So this is the first one, unrolling, get more parallelism. Any questions? Good, clear? Okay, so this is unrolling. Another thing you see a lot is partitioning, array partitioning. Again, nothing too complex, right? So we have a memory, right? So typically any arrays in hello synthesis will be synthesized to memory directly. But we could, like, for example, now we have parallel hardware. This is after unrolling, right? But we also like to actually read the values from our shift register directly, right? So by default, it's basically synthesized to a memory block. Then you can only read and write. one element every cycle. But here, since our hardware already parallel, we want to also do parallel accesses to our memory. So here, instead of having a memory module to store our array, so here, again, different vendor have different notations here. So basically, we can do a complete partition. It's basically complete partitioning the array into register. So every element has its own register here. So now with this, we can actually, now we can, so before even our hardware is, the on-road version of our hardware is parallel, but we cannot read enough data from memory. So it's still eliminating the performance. Now we can actually read like values from our shift register every cycle. So this is actually really when we get to a more parallel execution. So this is, again, partitioning. There are different pragmas of different ways of partitioning, like cyclic, block partition. We won't get to the details, but whenever you say, when people, hear people talking about partitioning, this is basically another way to actually expose parallelism. So this is partition, again, how we can actually get to a more parallel design. And finally, pipelining. This is actually, in general, auto pipelining. One thing at least in my experience, what I like about synthesis the most is basically doing this kind of auto pipelining in the design, so that you actually don't need to worry, like if the design is like something like this, very clearly can be pipeline partitioned, you can just let the tool to do the pipelining instead of actually explicitly manage how we handle pipelining in hardware. So that's one thing at least in my design experience, I find pretty useful, pretty handy actually when we actually do auto pipelining with a high-level synthesis tool. So here, right, so again with the FR filter, basically if we have like a sample coming in every cycle, we can actually establish this pipeline to actually have a more, basically higher throughput, so we can process all the inputs in parallel instead of doing sequential execution. So again, all of those have very clear hardware meanings, and here this different II. So always we basically want II is 1, basically this delta between sequences 1 and sometimes I see other people design with II like 2 or 4, but it's typically not ideal. In general, we want II is 1, just basically the intervals between different loop iteration interval is 1 to get a fully pipelined design. So this is loop pipelining. Again, like unrolling, partitioning, pipelining, those are basically 3 standard optimization to expose parallelism to get more parallel hardware. Again, there are other directives, but the most commonly used one, or at least from my experience, the most powerful ones are those 3 to actually get good design efficiency. Again, this is very simple introduction, but our goal here is to expose you to some of this kind of design flow, design alternatives, so that when you actually approach your design, or when you read other people's design, right? So now you actually interact with different designers, different flavors in the design process. There's nothing too fancy with all the different methodologies. They're just different ways of expressing hardware. So just a quick recap, right? So the goal of high-level synthesis is really, again, raise the design abstractions from RTL to some higher level. So here is basically C or C++ using higher level language, so that we can actually handle the growing complexity in the hardware. There are, as part of this module, design productivity module in this class this week, there are other alternatives. This high-level synthesis is not the only one, but we like to give you some examples, develop some iterations about what they're trying to do, what the different tools trying to do, and how you can potentially also interact with those tools, right? So specifically to high-level synthesis, again, to raise the levels of hardware design abstraction using higher level languages, C or C++, instead of Verilog, right? Use a more compiler-oriented approach so that we can actually use high-level synthesis tools or compilers to generate Verilog automatically. And another thing we see a lot, similar to the software development or like I guess Python development, we see now a lot of libraries these days, right? So there are also a lot of effort in actually doing this kind of more standardized libraries for hardware design, like Matching from NVIDIA. I know some folks are also doing like machine learning, ML about high-level synthesis libraries, basically having this more library-oriented approach so that we can actually reuse modules in the hardware design process. Again, there are a lot of interesting alternatives, a lot of different options, but high-level synthesis is one alternative in really thinking about design process. So before we move on to the next part, where we're going to cover Chisel and then later system Verilog, any questions about the design process in general, pros and cons, different tools, or anything you'd like to share with the class?
I have a quick question on enrolling.
Mm-hmm.
So can you, I guess like, I'm not sure I understand it. Can you like reiterate it a little?
Of course, a good question, Daniel. So here, unrolling is basically, as we mentioned, like it's unrolling this pragma is more specific to loops and basically unroll a loop. So let's use a Mac example here, right? So unroll, so we have a loop here, right? So we want to unroll the loop, meaning we want to have a flattened version of the loop so that instead of executing one loop iteration every cycle, so here, it's basically doing one Mac every cycle, whether we can do multiple Macs every cycle here. So unrolling is basically, you can think of instead of writing a loop here, you just manually write this multiple times. So like, let's say I is 0, this is one statement, and then you do another coefficient is 1 multiplied by, and then you do 2. So basically you have a, let's say, -1. You have we have an unrolled version of the loop where we basically, in a more software oriented way, you think of it like get rid of the loop, but to duplicate the statement. So you have multiple statements specifically for each loop iteration. This doesn't really make sense in the software way of writing a loop, because this way is just not very efficient, but it makes sense in the hardware because now every statement turns into a dedicated hardware component. So this is actually more like hardware microarchitecture. So now instead of we only have just the one Mac unit. So now we have actually n Mac unit, and then they have all of them can actually execute in parallel. So that's why it's called unrolling, but more from a software sense. But from a hardware sense, it's more basically duplicating hardware, duplicate the loop statement.
That makes sense. Thank you.
Good question. Any other questions or comments?
I actually had a few questions if the actual students don't, because I don't want to take anybody else's time. But so in the examples you gave, it seems to me that one of the strengths of HLS is you can first write what your loops are supposed to do, and then think about the microarchitecture after you've done that. But in actual practice, how likely is it that you'll have to change your loop beyond just adding pragmas at different parts to build the hardware you want?
Yeah, that's a good question. So this example is, I think, more on the simple end. It's just fairly straightforward, where we barely did any like changing the design from this to this. I think the only thing we did is basically adding this shift register from the original like algorithm implementation. In practice, especially when we actually get to more complex hardware, we do actually fairly heavy loop like design restructuring so that it actually get closer to the microarchitecture. Again, so still there are two ways of interacting with high-level synthesis tool. I mentioned briefly earlier. One is basically write the algorithm like this, and then just let the tool handle everything, and then add a bunch of pragma. For most of the hardware designers, I would recommend actually still start from understanding the microarchitecture. Think about what you want to design in the end. Well, for something like this, it's very easy. Okay, just unrolling pragma, unrolling partitioning, pipelining would actually get to where you are. But you still want to have basically what's the final hardware design you want to get in mind. In practice, when we actually get to some other designs, there could be more like things like explicitly have like registers. So here we only have explicit basic registers in hardware. Sometimes we also actually manually or explicitly declare like even temporal registers that we think to get a real design we actually need. So that also sometimes we also expose that in the C code. A lot of restructuring, especially with loop, is to actually to remove the cross iteration, the interloop dependencies, cross iteration dependencies in the loop. So a lot of time, sometimes just make it very explicit. There are no dependencies in the loop, or if there is, I try to actually strip away the dependencies as much as possible, so that you still need to have your vision of what a hardware looks like or can behave, and then you want to actually rewrite the code so that it actually goes closer to what the hardware looks like. I guess that's a high level gist, but in practice, a lot of, besides those pragmas, a lot of explicit declaration of registers or temporal storage, a lot of manipulation of the loops so that we don't have like cross loop, cross iteration dependencies. And a lot of time, like separating the loops instead of having nested loop, separating loop is basically, although we're not doing pipelining, we're structuring the code so that it's very clear to see what are the different pipeline stages, basically in a way. Those are the key at a very high level to actually get good performance. So if we want to get good performance, we still need to have a vision of what the hardware looks like.
I see. Okay, so there's partial separation, but not complete separation in practice.
In practice, especially when we actually want, especially when hardware designers approach this and want to get an efficient hardware design.
I see. One other question is, so it seems to me that you know, if we kind of ignore the fact that sometimes you have to change the loop itself, and you could just change pragmas, this could be like a very good platform on which to build like reusable hardware libraries, right? Somebody could write these implementations of these loops, and then the person importing that library can, like, with just one line, change how pipelined it is, or how unrolled it is, stuff like that, to kind of fit within their constraints. Do people do that in practice? Or?
Yeah, that's a good question. So like I also mentioned, I guess two things I mentioned earlier. The first one is like what you said, this can be easily changed so that we can explore different designs. So a very commonly used way of doing hollow synthesis is to actually explore the design space, right? So all of those we can actually insert in the code, but in reality, it's more like just tick a script, right? You can easily sweep those and then get different designs. So people do that to explore different alternatives. For the more library-based approach, so yeah, so those pragmas are one way actually to expose different, I guess more like a generator methodology, and like matchlib, and also the hollow synthesis ML library. So those are different pragmas, or different ways to expose I guess design alternatives, like especially when we actually get to more C++, more object-oriented design. So then you can do different classes, you can have different operands, different data types, different specialization, templated design. Those are another way to actually also leverage more, I guess more, this is less related to C, but more like if we can also use object-oriented design style to get more generator style approach. So those are, I think, also heavily used in those libraries to actually get more reuse out of high-level synthesis code. Okay, great. Good questions, good discussion. Anything else people like to share, ask? Okay, great. So with that, again, this is just a high-level introduction. A lot of cool things, a lot of public available resources, and also open source high-level synthesis tools will be fun to play with if you are interested in the methodology. So next, we're going to transition to the Chazal module there. So maybe because it's easier, you drive on your end. So let me actually pause recording. Okay, go ahead.
Okay, so now that Sophie has talked about high-level synthesis, which at least partially raises the abstractions from the actual RTL up to the algorithms, we're going to look at other ways of writing RTL that aren't HLS, but that might still be more effective than traditional traditional RTL languages like Verilog or VHDL. So in particular, we're going to focus on Chisel. Chisel is a language that was developed here at Berkeley to write RTL efficiently. I'm going to talk about what I like about Chisel, maybe some issues that Chisel has that you might run into if you're using Chisel, and how it compares against existing hardware description languages. Yeah, so before we dive into Chisel, let's kind of look at the state of the art a little bit. You guys probably already have some experience with Verilog and VHDL and maybe System Verilog, but we'll look at a little bit at the history to see where existing HDLs fall short. So first, there's Verilog and VHDL. These are the two most famous hardware description languages. They're some of the oldest, some of the most popular. And if you ever get a job in industry writing RTL, it will probably be in one of these, or maybe in System Verilog. But despite their very vast market penetration, they have some issues that have been known for a long while, right? Which can reduce the productivity of people developing with them. One issue is that it can be hard to parameterize your code when you're doing it in Verilog and VHDL. So with Sophia's HLS examples, you can see how you could just change a few variables and get different hardware designs that still do the same thing. It's harder to do that with directly in Verilog. And some companies get around this by writing scripts which generate Verilog, which is you can think of that kind of like designing maybe a very, very simple domain-specific language to generate Verilog. But if Verilog itself was better at this, this wouldn't be necessary. Verilog is not very type safe. I believe HDL is a little bit better in this regard, but Verilog has some issues with type safety. The notion of signed and unsigned data is a little bit maybe hard to understand sometimes. And the type safety makes it very easy to accidentally mix signals you shouldn't, or accidentally truncate bits you shouldn't, or accidentally cast multi-bit values to Boolean values. And then fixing these bugs later is annoying. Another issue is that for a beginner, it's very easy to actually write Verilog and VHDL that can't actually represent real hardware. And the reason for this is that these languages were originally simulation languages, and CAD tool designers later realized they could infer hardware primitives from the description of the simulation. But the developer is really describing a simulation, not hardware, and then the hardware is being inferred. And if you're not experienced with this, it's possible to write a simulation that actually doesn't describe hardware that you can implement with existing CAD tools. Or maybe you'll write hardware that can be implemented, but is not what you wanted. Maybe you'll accidentally write memory that has way too many ports. So developers end up having to follow very specific coding standards while writing their code. And because of this, there's a huge market for Verilog linters, right? People sell tools that will check your Verilog, kind of get around some of these issues that exist with it. But if these languages didn't have these issues in the first place, linters wouldn't have been necessary. So this is a quote by Dan Liu. He used to work at Centaur Technology in Austin, Texas, which develops basically a cheap x86 cores. They're one of the only 3 companies in the world that are allowed to build x86 designs. He has a blog post where he talks about hardware description languages a little bit. In one part, he partially criticizes Verilog. There's a quote from him here where he's kind of thinking out loud, and he's saying that people who are very experienced with these languages will tell you that all of these issues are fine. You just have to get more experience. You have to learn better how to do it. It's the developer's responsibility. But maybe this points to issues that exist with the languages themselves that should be fixed. So another very I guess the third big HDL out of the big 3 is System Verilog, which is a superset of Verilog, which adds some new features. These features are especially useful for verification and also make it a little bit easier to work with different data types, right? It lets you raise your abstractions a little bit. It also has support for object-oriented programming. I don't know that much about System Verilog myself. I have not used it, but Vignesh, another student, will describe more to you guys about System Verilog in a future lecture, so you guys can ask him. Although it's got some advantages over Verilog, it's still got some issues. It's still possible to generate non-synthesizable hardware by mistake, especially if you're a beginner and you don't have maybe an experienced mentor. And it also has some more advanced exotic features that aren't always supported by all vendors, right? And you don't want to be locked into one specific CAD tool vendor. So this is where Chisel comes in. It's a lot younger than these other languages. It's developed at Berkeley, and it tries to resolve some of the existing issues that exist with some of these other hardware description languages. So unlike Verilog, VHDL, and System Verilog, Chisel is an embedded language. So that means Chisel is actually a language inside of a general purpose language called Scala. With Verilog or VHDL System Verilog, your compiler reads a Verilog file directly. With Chisel, rather, Chisel is more, you can think about it more as like a library implemented in Scala to help you describe hardware using a general purpose language. So the main insight behind Chisel is that you use this Chisel library to describe your hardware, and then you use the full power of this general purpose language to parameterize your hardware across lots of different designs, right? So the general purpose language manipulates the hardware descriptions that you've had. And this means you don't really just have to write specific circuits anymore, like individual circuits, individual hardware designs. Rather, you can write programs that will generate a whole class of hardware designs based on your parameters. And this can be really useful. There's other advantages it has. It has no separation between synthesizable and simulation-only hardware. Because it didn't start as a simulation language. It started as a hardware description language. So that's all it does. It's very easy to define new types and even type classes, which is a more advanced feature that exists in some languages. So you don't have to think in terms of bits, you have support for operator overloading, implicit data type conversion. You're able to think in higher abstractions. You're able to reduce a lot of the scaffolding work sometimes you have to do related to types. And you have a very strong type system within the Scala language that will make sure you don't get errors during the compilation stage before you get to simulation, which can save you time. But obviously there are catches as well. Chisel isn't perfect. So I've listed some issues here with the language itself. Later on in the slides, we'll talk about some issues with the Chisel compiler, but I'm trying to separate the actual tools that ingest Chisel and the high-level Chisel language itself, which the developer will be working with. So some issues with the language itself is that although it has support for asynchronous designs, the support is kind of awkward right now. It was originally designed to be a synchronous hardware generator language, and that kind of, those assumptions seep in very low. So support for asynchronous hardware is possible, but kind of awkward right now. But maybe it'll improve in the future. The verification flow is not yet as advanced as it is with System Verilog, right? There's decades of work building verification libraries with System Verilog. That hasn't happened yet for Chisel. So we have lots of smart people here at Berkeley and at other universities who are actually working on this, trying to improve the verification flow. But right now it's not as good, and this can be a deal breaker for some designers because verification is typically one of the most painful parts of designing hardware. Another issue is some people just don't like working in Scala, right? So I don't know if you guys have even heard of it. Some years ago, Scala was like the hot new language, right? There was a lot of hype around it. It's still a great language. It's still got a lot of users. It's still popular, but the hype has died down a little bit. A lot of people now, when you tell them you have an embedded language for hardware description, will ask you why you didn't do it in Python, right? Hardware designers also generally are not often the most software savvy people, so they may not know all of these more exotic languages. And another issue beyond the Scala language, the fact that it scares some people off, is that the Scala ecosystem can be a little bit painful to use sometimes, right? You're relying upon the JVM, you're relying upon certain build tools. Some of these can stress a cheap laptop out, right? Okay, and I've described 4 different languages, but I just want to make it clear there's lots of hardware description languages out there, right? The Chisel developers weren't the first ones to look at the existing state of the art and say, oh, we should do something else. Universities, hobbyists, industry people have come up with lots of different languages, hardware description languages. Most of them are like Chisel are embedded languages. They're not standalone languages. And if you just can't get over the fact that it's in Scala, you have options in Python or Haskell. So if you don't like Chisel, don't let that turn you off from this world of exploring HDLs outside of Verilog. I've given some examples here. This is completely incomplete. There's lots of them, like I said. Some of these are hobbyist projects like Smile HDL. Some of them come from other universities like BlueSpec, which came out of MIT. There's a lot of stuff there to explore. Some of them do some things better than Chisel. Some of them do some things worse. It's a matter of opinion. Okay, so now that I've kind of made maybe the elevator pitch for Chisel and talked also about some of the issues with it, let's go into some example of Chisel code so you guys see what you would be working with if you were working in Chisel. So we can look at a FIR filter example, like Sophia showed earlier with HLS. Now, if you're a beginner Chisel user and you're trying to design this FIR filter, you'll probably write what we call prettier Verilog, where you use Scala's more, I guess, aesthetically pleasing syntax to write code that really semantically is not anything different than what you could do with Verilog. So over here, we've described a very specific FIR filter, a 3-point moving sum. Right? You can only handle three values. It's parameterized across the bit width, but this is very simple parameterization. Verilog could do that as well, right? But if you're starting out learning, there's nothing wrong with writing Chisel like this. This is how I wrote my first Chisel designs as well. But where Chisel really shines is when you kind of step up a few levels of abstraction, and you think maybe I shouldn't just describe specific circuits, I should write generators for circuits. So over here, we have a generalized FIR filter where I'm not only doing 3 different values anymore. I'm allowing it to have many different values. And these values are basically a constructor parameter, and I can have as many of them as I want or not want. I can instantiate hardware that's large or small, right? Chisel makes it easy to do that, and Chisel encourages that. And that makes your hardware more reusable in the future. Another advantage of Chisel is it makes functional programming easy, right? So some functional programming constructs you'll see here, reductions, maps. It's very easy to use those kinds of constructs if you like functional programming, but it doesn't force functional programming on you. So there's also for loops here. Stateful statements are okay in Chisel too, right? It lets you choose. And if you want to do functional programming, it lets you ease into it slowly. Another place where Chisel shines is support for playing with types. It supports type classes, which not every language does. Great type checking, very, very good type system in general, which comes from Scala. That was mostly implemented by the Scala people, which helps to reduce bugs. So previously in the last slide, I had only parameterized across the bit width, and I was only operating on unsigned integers. Here I'm saying this can be any basically numerical type which fits within this ring data type class. So I could have designs that work on floating point unsigned integers or signed integers or fixed point numbers or floating point numbers or whatever, any data type which conforms to this type class. And I can support, moving 3-sum filters or delay filters maybe, where I'm not really multiplying, I'm just delaying data. Triangle filters, all of this, right? So this helps to make your hardware more reusable. So later on when you need another FIR filter, you don't have to write a whole new circuit, or you don't have to change the source code to the one you want to have. You can just reinstantiate it, and you can even share your designs with other people in libraries. So you've kind of seen some of the things maybe that I could tell what I personally like about Chisel by what I emphasized. Because of this support for functional programming constructs, list manipulations like maps, reduces, scans are very easy, and I find that it allows you to write code that's both more terse, but also more clear and expressive sometimes than using for loops for everything. Parameterizing across types is very easy, like we showed. It's easier to write reusable hardware than it is with some other languages. There's some examples of this. There's a very convenient standard library in Chisel, which has small hardware designs like queues, handshake-based interfaces, and bit manipulation functions, counters, which will just work even if your application is very different than what the original standard library designers had in mind. And there's libraries like third-party libraries like Rocketship, which have been written, which have components that are kind of plug and play, right? So in my own hardware design, I guess, journey, I had to use TLBs, but I didn't write my own TLBs. I just instantiated TLBs that were written by other people. Caches, entire CPUs, you can kind of plug and play them. And one thing that maybe you don't see in the examples earlier is Chisel has very excellent IDE support. You don't have to just work in Vim. You can if you want to, but you don't have to. You don't have to work in these kind of arcane IDEs that Xilinx will sometimes give you. You can write code. You can write hardware in IntelliJ, and not every language lets you do that. Okay, let's see how much time we have left. Okay, let's go through these quickly. So we've seen some examples of how Chisel code looks, but you might be wondering how that actually gets turned into hardware, right? So it happens through several steps. Your Chisel code does not directly get converted, doesn't directly get compiled down to Verilog. Rather, it passes through an intermediate representation called Fertile. So if you guys don't know what intermediate representations are, you may have heard of them in the software world. So you can think of Chisel as a compiler or language like Cling, which is a C++ compiler on Mac computers. You can think of Fertile as an intermediate representation like LLVM, which is very famous now. And you can think of the final Verilog that's generated, which you actually feed into your synthesis or place route tool as the actual machine code, right? And you might wonder, why do this? Why add one extra step? Wouldn't it be easier to just go directly from Chisel to Verilog? Well, this actually has some of the same advantages that LLVM does, right? So you can have multiple hardware description languages, including ones that didn't come out of Berkeley, but came from people at other groups, which target Fertile. And then the Fertile can support multiple different, lower level languages. Then somebody who wrote Magma wouldn't have to write a layer that does Verilog and VHDL themselves, but could just target one single intermediate representation and get the support for all these different languages. In practice, actually, although Magma does, I think, compile down to Fertile, if I remember correctly, Fertile only compiles down to Verilog right now, but VHDL support could, in theory, be added. But other than this multiple language advantage, there's other things Fertile supports. You can do transformations on Fertile. You can write programs which will directly change the abstract syntax tree of Fertile. And again, this is an idea that exists in the software world as well, right? Compiler transformations for your software code will do the same thing. And this means you can write your hardware in maybe a higher level of abstraction with Chisel, and then somebody else can write a Fertile transformation, which gives you early area estimations, or which adds hardware counters and instrumentation to your design without you having to add them yourself when you're designing your hardware. Or you can optimize your actual hardware for ASICs or for FPGAs, which might have different optimization requirements without you having to explicitly do that yourself in Chisel, right? So these, you can use transformations written by other people. These optimization passes, they can be shared across hardware designs, right? People have made lots of very useful transformations, right? They've made transformations that build test harness generators, macro compilers, which are very useful for mapping to SRAM, simulators. I've never written a single Fertile pass myself, but I've benefited from all these other people's passes, and they've saved me a lot of time, especially with tests and compiling stuff down to SRAMs and stuff like that. If the person writing the Chisel doesn't even have to know Fertile exists, but if he wants to, he can interact with it himself. He can attach any metadata he wants to any Chisel expression, and the Fertile compiler can pick up that metadata later. And this allows more fine-tuned optimizations if the Chisel designer wants that, although it's not required. Okay. So there's a lot of advantages to this two-step process and to these transformations and compilers that other people have written. There are some issues, right, that I'll mention in the interest of fairness. The final Verilog that's generated can be hard to read sometimes, especially if you have arrays, I found, and sequences. Those will usually be fully unrolled, which can make it harder to read them. This can make debugging and verification more difficult, especially for some automated verification tools, which were originally designed to be used with Verilog that is human readable, that looks like how a human would write it. And they may not work as well with this type of Verilog. There's some other hardware description languages in the list I gave earlier, which do a better job of generating human-readable Verilog. And another issue is that the compiler can be kind of slow. It can take you several minutes to get your final Verilog out, whereas if you wrote in a system Verilog, it would immediately be ready. And it can be very memory hungry, right? So in my freshman year, I actually used to develop, I used to compile Chisel code on my own laptop. I would, be in lectures, not listening to the lecture, just writing, working on my research. And I would not be able to compile the actual code because if I did, my laptop fans would get so loud that it would like attract attention, right? So it's memory hungry. It can be stressing on a low-end computer, but I think people have been working on optimizing that too. Okay, so we're kind of nearing the end here. So I've kind of made the pitch for Chisel, right? And also described some issues with it. Hopefully you think that the advantages outweigh the disadvantages. But even if you think Chisel is great, you might worry that there's no point in learning it because you'll be the only one using it, right? All your friends will be writing in Verilog. But if you're at Berkeley, your friends probably have used Chisel. At least somebody has probably used Chisel. Chisel and Fertile are an integral part of what I call the Berkeley stack, which is the integrated set of tools that Berkeley has created to make it easier for people to create their own hardware SoCs. So people at Berkeley have used Chisel to generate different CPUs, right? Both in-order CPUs, which have become have made a big splash. Out-of-order CPUs, which have competitive performance with some commercial cores, educational CPUs, different accelerators, right, for vectors, DNNs, genomics, right? So across different application domains, protobuf accelerators, which are used to tackle some of the what is called the data center tax, some of the overheads of running data centers. People have used Chisel to design hardware design frameworks like Chipyard, which apparently you guys have heard some stuff about, as well as simulation frameworks, which use Fertile transformations, like FireSim and Midas, right? I've developed hardware for the past few years here at as part of my PhD program, and all this other tooling that was built partially on Chisel has been a big help in making me work faster. Okay, but even if you think people outside of, even if you agree that people in Berkeley use Chisel, you might be worried that nobody outside of Berkeley will use Chisel, right? You'll learn it, and then as soon as you graduate, you'll never touch it again. So it might not be worth spending time doing it. But this isn't true either. There are people both in industry and in academia outside of Berkeley who have used Chisel. Obviously, it doesn't have anywhere near the market penetration that Verilog or VHDL has, right? So I'll be completely upfront about that. And if you graduate, you'll probably still write in Verilog or HLS or System Verilog or something like that. But there are both companies and universities outside of Berkeley using it, right? Google kind of famously designed their Edge TPU in Chisel. There's different companies and universities across the world, right? So this is actually a startup in Pakistan, right? All the way in Pakistan. This university is all the way in Europe, China, right, and across America. So so niches do exist, and if you work for Sci-Fi, which is a startup which came out of Berkeley, they do a lot of their work in Chisel too. Oops. Okay. So do any of you have any questions to ask me about all of that?
Hey Hassan, can I ask a question?
Yeah, sure.
I was wondering, in the first part where you talked about different programming languages, I was wondering in particular, like System C and Chisel, they're both embedded libraries of another programming language. How do these two compare, and what advantages does one have over another? Or are they altogether addressing different problems?
Yeah, so I am not a good person to ask that because I have no System C experience at all. Maybe I should have made a slide for that too. I guess I didn't think about that. I think System C is more of a simulation language, right? Maybe Sophia knows more.
Yeah, maybe you can. Oh, I can talk a little bit more on the System C front.
Okay.
Sure. Yeah. So system C. So I actually didn't get to mention system C in the high-level synthesis part, but a lot of actually today's high-level synthesis is actually more focusing on the system C, actually using system C. So when we say C, C++ or system C, actually system C is actually being used a lot more often in high-level synthesis. Maybe less about comparing systems. Maybe it would be interesting to do system C and the system Verilog comparison. See, let's say how system C is actually used in high-level synthesis world. So first, it actually, as you mentioned, it has actually more like a different timing, or more, it's basically a C++ library, right? It has actually more hardware specific timing, again, originally for verification, but also can be actually very used for the design side. So a lot of the time, the model in high-level synthesis actually designed using system C. And typically when we actually use high-level synthesis, especially design more complex module, system C is basically almost like the default language to be used, especially with a lot of like basically the way it handles clocks and the way it handles interfaces. All of those are actually very, very useful. Another benefit of actually using system C as design language is that it can also be used as verification language in a way. So I mentioned earlier when we do the design process, when we actually do the C++ or C++ level design and testing, more specifically what I meant was actually system C level design and testing. So we do almost the majority of our verification testing in system C, and we can actually just use C++ standard testing infrastructure to do actually the standard coverage analysis, more software-oriented coverage analysis, which has actually also be very, very useful and very interesting. I guess more specific to system C versus Chisel comparison. I think that's a very, very interesting question. Still, it does have a lot of library support with system C, but system C is still more used as a like high-level synthesis way of doing hardware design, versus Chisel is actually still, at least my view of Chisel is still a RTL design language. It has like interesting structures and features, but it's still more like a RTL level design. So there's still two level different design abstraction there, but both have actually interesting other features and library support, which makes the design easier. That's my take. Hassan, what do you think?
Yeah, I mean, Chisel is, I don't think it's HLS, even though it gives you some of these higher abstractions. But even with the higher abstractions, at some point somebody is dealing directly with the gates, with the RTL, the flip-flops. Yeah, I don't know enough about system C in particular to say, unfortunately.
Got it. Thank you, Professor. Thank you, Hassan.
Can I ask a question?
Yeah.
Yeah. So Hassan, you mentioned that the way the Chisel language translates into Verilog is not very human readable, and it's different from what we usually write. So I'm thinking like of a simple example, like maybe we're writing a counter in Verilog. How different would that same counter look if it was coming from Chisel? And like, would it be very different? Because I don't know how a counter can be written in like a very simple counter can be written in a very different way.
Right. So a counter is a very simple design, so that would probably not be too different. In practice, I found that for debugging, finding signal names, if you open it up in a waveform, is also not difficult. The main differences I found are, first of all, Chisel likes to, Chisel, the protocols unroll things which don't really need to be unrolled, right? So working with arrays can be kind of painful, because you can't just pull up the array in your waveform viewer. Every single element has now been separated. Chisel also generates a lot of intermediate variables, right? A lot of intermediate variables that don't really need to be intermediate variables. It separates oftentimes almost every operator into its own intermediate variable. So when if you're reading the Verilog directly, it can be sometimes hard to see exactly how a variable is set, because you have to go through a lot of other intermediate variables to find how it's set. But that's only an issue if you maybe don't understand your own Chisel code and don't understand how that variable is set in your own Chisel code, which happens very rarely, but I've had times where I had to kind of look at the Verilog, but that's very rare. Another issue I found personally, I think sometimes it uses structural code where I would have used behavioral code, and sometimes it uses behavioral code where you would have used structural code, which can make it also a little bit difficult to read the Verilog file directly. And there are some parameterization. Verilog does have some support for parameterization, especially simple parameterizations like bit widths, but Chisel kind of unrolls every single parameterization into a different module. So things that could be just one module with like a constructor parameter all become different modules with every different constructor parameter. And that can explode the size of your file and also make it a little bit more difficult to search over.
Okay.
Does that help?
Yeah, just a follow-up question on that. So last semester, I think most of us were working on this huge RISC-V design project. So I was thinking, if we had done that project in Chisel without using like off-the-shelf libraries like Rocket or something, so would the design effort be lower, and would it be easier to build the same specification?
What design project?
Oh, actually, we were building a 32-bit RISC-V processor for the 251A section last semester.
Okay, so I actually did that in Chisel, right? The CPU and the cache, because I was a grad student, so I had to do a cache as well. I wrote those in Chisel. So one immediate advantage that Chisel had over Verilog there was that Chisel actually caught a combinational loop we had, which our Verilog compiler did not catch. Our design would just hang and we couldn't find the design, right? We couldn't find the loop, but the Fertile compiler with these passes actually ended up finding it. So that was a very immediate, maybe corner case advantage we had, but that saved us some time. So that was one advantage. So this tooling, right? We were able to use the tooling a little bit to find a bug. But one issue is when you're doing a homework assignment, you're not being graded on building a generator, you're being graded on building one specific design, right? So you're not taking advantage, you don't have to take advantage of all the meta programming and parameterizability that Chisel tries to encourage you to do. So your advantage would have been lessened there. But you would have still, I think, gotten, the clearer syntax, the list manipulations. List manipulations are more useful, I think, for parallel accelerators. For CPUs where everything is happening one after another, they're not as useful because you're not working with arrays as often, more with just scalar values. But yeah, so that's kind of an inconclusive answer. I don't think it would have been a big help. It helped us find one particular bug, but it would be more useful if you were, so at least the selling point behind Chisel, right, the elevator pitch is that it would be more useful if you were designing a CPU that you wanted to come back to later again in the future and use again for a different project.
Okay, that makes sense. Thank you.
Maybe just one more comment here, Satoshi. Very good question. And what Hassan mentioned there actually also apply to generally a lot of the different design like new design tools and the flows, a lot about the reusability and portability. If we do everything designed from scratch and we just use that instance, it's less useful. But even in industry practice, there are like some module that has been actually used across generations of hardware, like some different kind of crossbars, different modules. And they get to the point that only very small number of people actually understand the internals of it because it's heavily optimized, tailored to specific things. And with that, it's just very hard to maintain, to change, to debug. And with some of these newer level of abstractions, of course, there's just design a specific instance part of it, but also really reusability. We actually want to reuse it, making sure more engineers can actually understand it and also can use that to generate different flavors of design instead of just generating a single instance. Those are typically where this kind of more generator-based, highly parameterized design methodology shine because the design is more, not necessarily more complex, but more reusable. Mm-hmm.
Okay, thank you, Professor. Thank you, Hassan.
Mm-hmm.
We're out of time. I also wanted to kind of leave you guys with some questions to think about, right? Maybe flip the tables a little bit. Since we're out of time, I'll just go through this quickly. One thing you guys should kind of be thinking about is Chisel focusing on the right problems, right? Not everybody agrees that it is. One of the HDLs that I gave earlier, one of the designers of that actually has a blog post where he kind of rips Chisel apart. And he argues that Chisel just completely misses the mark because he believes that logic generation is a solved problem. It's not hard. The real hard thing is verification. And Chisel makes logic generation easier, but he doesn't think that's important. and it doesn't make verification any easier. So he thinks there's no point in switching over to it, right? So that's his opinion. So you should be thinking about that too. Another thing maybe to think about, a lot of people complain about Verilog and VHDL system Verilog. You can find a lot of blog posts about it online, but they still keep using it, right? So maybe maybe there's a revealed preference over there. Maybe it's not as bad as people are saying, right? So I'm kind of just trying to push back on stuff I said earlier so I don't come across the chisel shill. Another thing you might want to wonder, is it even worth creating new hardware description languages at this point? Sophia showed us HLS. A lot of companies are using HLS, right? So why not just make why not take all these smart people who have been working at Chisel and make them focus on making HLS compilers better, right? So there's reasons why they didn't do that, right? Maybe it's just impossible. Maybe it's just so much, it's not worth the effort. Maybe it's better to just create a better HDL so you don't need all these HLS tools. But that's a matter of opinion. And maybe something else to think about is what other abstractions other than HLS and RTL level are possible for generating hardware, right? Maybe you could make a CPU design language, which only designs CPUs, but it's not as general as HLS. It's not as low level as RTL, but it works very well for CPUs and makes people design CPUs faster. Maybe you could build one for accelerators, right? This isn't the end of the road. Hardware design will change in the future, and it continues to evolve, and you guys maybe should think about how you think it should evolve. And that's the end of my
Okay, wonderful. Well, thank you very much, Hassan, for sharing your Chisel experience, and thanks everyone for participating in the discussion. So we're at the end of this lecture, but we'll have more discussion next week. This Thursday on System Verilog. So great to see you all here today, and I'll see you very soon. Take care. Bye.